So we are going to explain one of them in full detail, if you like, one of these famous functions, and then we can give you the formula for the rest. In calculus, inverse of the sine function and the tangent function are going to be much more important than the other one. Okay, so what is going to be the inverse sine function? Okay, what's going to be the inverse sine function? Just give you a little bit more detail to understand that for this function. So we just recall that if you have recall that the graph of the sine function, the graph of y equal to the sine x is going to be given by, so that's going to be the one. You know that this is going to be the sine function. So if you want to consider the one period, it's going to be the 0 and the 2 pi. As we did in pre-calculus, so we divide it into 4 parts. It's going to be the pi, and that's a pi half, and that would be 3 pi half. And the sine at most, it can be equal to 1. At least it can be equal to the -1. So the sine of the 0 is 0. So this is the way we are going to get it. We start with the 0, we go to the maximum, which is 1. We go to the intercepts, then we go to the minimum, which is a -1. So that's a 1, -1, then you go to the 0. So this is how you get the graph of the sine function between 0 and 2 pi. If you want to continue, just, like looking into the mirror, you can get the similar on this part. So this is going to be -2 pi. And the middle point is going to be -pi. Then you have a -pi half and a -3 pi half. Okay, the same thing. If you want to continue, you start from here, you go to the minimum at 1 here. So we get the minimum, then we get the intercepts, then we get to the maximum, and then we get to the 0. It's just going to be the copy of the other part. So this is going to be the graph of the sine function. You see? In order to find the inverse of a function, you know that this function must be the so-called one-to-one, which means when we get the inverse of the function, we switch x and the y. So if you switch x and the y, is like, looking at the function in this format, if you like. That is going to be the case. Then when you switch x and the y, you must guarantee that the result is going to be a function. You know that when y equal to the sine x is a function, each vertical line will intersect the graph of the function at one point only. Okay, so that's the definition of a graph of the function. So if you consider the inverse function, you switch x and the y. So this vertical line would be changed into the horizontal line. Okay, that make it a horizontal line. So if this function would have an inverse, each horizontal line must intersect the graph at one point only. But as you can see, this horizontal line would intersect the graph at many points, or 4 points. So this function is not invertible. So this means if you consider the sine function or any other trigonometric function in their natural domain, they are not going to be invertible, because these functions are periodic, and you know that after an interval, this graph would repeat itself. For the sine and the cosine, the period is 2 pi. For the tangent, is pi. So that's why you've got to be very careful when you want to find the inverse of these functions. So in general, this is not going to be invertible. So in general, y equal to the sine x has no inverse. No inverse when, let's say, x is going to be one period. X is going to be between 0 and 2 pi. So what we're going to do, we are going to restrict the domain of this function. You have to restrict it so this graph won't have any of this property. So there are different ways to restrict it. One way that we can restrict it is just consider the graph in this interval only, you see, between the negative pi half and the pi half. So if this is going to be negative pi half, sorry, and that's going to be positive pi half. So this is going to be 1, and this is going to be a negative 1. So your graph, as you can see it over here, is going to be coming from this part, as you would end up with a 1, 1. So this would be your graph. Now, as you can see, if you draw any horizontal line, that would intersect the graph only once. So this means the inverse of this function, the inverse of this function does exist, and the inverse is a function. You see, the inverse of a function in general is a relation. You have seen this type of, you should have seen it on, during your pre-calculus class. And so this means if you put y equal to the sine x, when x is between pi half, negative pi half and the pi half, then the function has an inverse. Then the sine function has an inverse. So that's a difficulty about this type of function, and you must know it because we are going to use it at the end of the course again. That the sine function would be invertible only if we get this, this restriction. And you have to do the same thing for all the other trigonometric function. So now that would make us ready to define what is going to be the inverse sine function. Okay, so that's the definition. The inverse sine function is going to be denoted by y equal to sine inverse of x. It's not the power, it's just a name. Or we are not going to use this notation, or sometimes they use the arc sine notations. Arc sine of x. It's the same, but there is a difference really. So it's a very old-fashioned notation. I'm not going to use this notation. But if you see it in your book, so you realize that it's the same as the inverse function. Okay, so the inverse sine function is denoted by equal to the sine inverse of x. And I'm going to define it. And is defined by, that's it, y equal to the sine inverse of x. If and only if you switch it, x is equal to the sine y. Okay, that's the definition of the inverse function. Your function is already solved for y. So if you can solve it for x, that will tell you that you have that inverse. But there is a restriction. The restriction is going to be when this y, as we talk about it, must be between the pi half and the pi half. And then x is going to be the range of the sign. It's going to be between -1 and 1. Okay, so that will tell you that the domain of the, so therefore, y equal to the sine inverse of x, when x is, the domain is going to be close interval of -1 and 1. Okay, so that's going to be definition of the sine inverse of x. When you are in pre-calculus, you'll be given different numbers for the x to find it, but in calculus 2, if you want to find it, you can use your calculator. So we're just focusing on the function nature of this famous function. Okay, so that's the definition of the sine inverse. So what we are interested in, we are interested in derivative of this function. So I'm going to differentiate it. Okay, it's very easy to differentiate it because as we did it for the exponential function, so this is how we're going to arrive at the formula for the differentiation. So look at this one. Note that if you have a y equal to the sine inverse of x, we switch it, x equal to the sine y. So what we would like to do, we'd like to find the y prime, derivative of the y. So differentiate these sides. So you have the x equal to the sine y. Differentiate respect to the x. Derivative of x would be 1. You have sine y, derivative of a sine is cosine. Cosine of y, but you have to multiply by y prime. Chain rule. Okay, it's a composition chain rule or implicit differentiation. Whatever you like. Okay, so that's it. So we find the y prime. Y prime is 1 over cosine of y. What do you want to write down in terms of the x? So we go back, we say, oh, bet x equal to the sine y. And remember this formula from trigonometric function or the identity, particular identity. This is equal to 1. And so sine y is x. So that gives you x squared equal to 1. So the cosine squared is 1 minus x squared. So the cosine of y is going to be positive or negative a square root of 1 minus x squared. But remember the y, that the y is between negative pi half and the pi half. So this means y is in the second quadrant. Y is here. It's between negative pi half, you see that's a positive pi half and the negative pi half. So your angle is here. And in both cases, the cosine is always positive because this is going to be the cosine of y. So the cosine of y is positive. Therefore, cosine of y is going to be equal to the 1 minus x squared only. Okay, that's why we pick this domain for the inverse function because of this type of idea. So, but the y prime was 1 over cosine of y. So it's going to be 1 over the square root of 1 minus x squared. But remember the y was sine inverse. So you prove very important formula. Derivative of the sine inverse is 1 over the square root of 1 minus x squared. Very popular formula for the rest of the course. I just proved it so that you know, you believe it. And you find out when we arrive at this formula. You don't need to know the proof, but you need to memorize this formula. This is going to be a very popular formula that we have. Okay, so we can write down as a theorem. The theorem would be, there we are, part 1, the derivative of the sine inverse is 1 over the square root of 1 minus x squared. But if you have a u function, as usual, you have to apply the chain rule. It's a composition of two functions, the sine inverse function and the u function. The derivative of the sine inverse is 1 over 1 minus u squared, but you have to multiply by u prime. So it's going to be u prime a square root of 1 minus u squared. Okay, again, very popular formula. So make sure you remember this formula, derivative of a sine inverse, 1 over a square root of 1 minus x squared. It's going to be, if it's going to be anything else, okay, it's going to be anything other than the x, you see x squared, 5x, 7x, then you have to apply the chain rule and multiply by u prime. Okay, so whatever you do for the derivative, you are going to have for the integral too. So in the form of the integral, that is going to be the case equivalently. Equivalently, you are going to have this one if you have an integral of dx over the square root of 1 minus x squared. This is going to be simply sine inverse of x plus c. Again, very famous formula. As soon as you see this integral, you should be able to recognize it, that this is going to be the sine inverse one. And if it's going to be u form, anything other than the x, we are going to call it u. So it's going to be the square root of 1 minus u squared. So that gives you sine inverse of u plus the constant c. Okay, so this is all we have to know about the sine inverse, integration and the differentiation. Okay, you can write these formulas and bring it to the test, we don't mind, because there are going to be quite a lot of formula that you have to know, you have to memorize in this course. So your job, if we give you one question on your next quiz, a function to differentiate with the sine function. So the first part, find the derivative okay, find the derivative of each function. There are going to be kind of two types of problems, okay, that we're going to have. Okay, so this is it, the first type. And no chain rule, but you may have to use the product rule as we did it before. So the function is going to be f of x equal to the x to the third times it by sine inverse of x. Okay, it's going to be a powers of x times sine inverse, x squared to the fifth to the sixth radical x. So it's type of problems. Okay, as you can see, it's a product of two functions. The first function is x cubed, the second function is sine inverse. So you remind yourself that you have to use the product rule. Okay, this is it. So derivative of the first one, f prime, times the second one plus derivative of the second one times the first one. Okay, so you recognize the formula and then you just do it. So what's going to be the solution? F prime equal to derivative of the first one, derivative of the x cubed would be 3x squared times that by the second one, times that by the second one. Okay, plus derivative of second one, sine inverse. Derivative of the sine inverse is 1 over s square root of 1 minus x squared. That's the derivative of the second one. Times that by the first one. The first one is just x cubed. Nothing to simplify. So the final answer is 3x squared sine inverse of x plus, on the top we get the x cubed, and on the bottom is going to be 1 minus x squared, and you're done. Okay, so it's a product of two functions. So we apply the product rule to differentiate it. Derivative of the first one, derivative of x cubed is 3x squared times the second one, sine inverse, plus derivative of the second times first. The second one is sine inverse. So the derivative is 1 over radical 1 minus x squared times that by the first. No chance for simplification, and be done. Okay, so that's going to be the type 1. Type 2, you need the chain rule. So that's going to be the type 2. The type 2, like g of x equal to sine inverse of x cubed, for example. You see, it's not sine inverse of x, it's sine inverse of something else. So it's like sine inverse of u, if you like. Okay, remind yourself, solution. Just for your information, you may think about that the u is x cubed. So your g of x would be simply sine inverse of u. Okay, so the g prime of x is going to be u prime over the square root of 1 minus u squared. When we get the chain rule, there is going to be an extra term. That extra term is going to be your u prime. Now I substitute. So g prime of x is equal to u prime. U prime derivative of the x cube, which is a 3x squared, divided by the square root of 1 minus u squared. U is x cube. So x cube squared. So it's going to be 3x squared, square root of 1 minus x cubed squared would be x to the 6. And you're done. Okay, don't miss it. When it's not going to be sine inverse of x. Whatever it is, you are going to call it u. So u is going to be x cubed. It's a chain rule. So derivative of the outside sine inverse times derivative of the inside. Derivative of a sine inverse of u is 1 over the square root of 1 minus u squared. But you have to multiply by u prime because it's a chain. So that's it. U prime is 3x squared. 1 minus u squared. U is x cubed. So 1 minus x to the 6, the final answer. Okay. So that would be the case. There is one. Sorry, I got that kind of allergy for my voice, or just a little bit cold. So there is one famous one, and that would come with the radical x in calculus 2. You may see sine inverse of radical x, and tangent inverse of radical x, secant of radical x. So you got to be careful about this one. So that one too. Okay. So that would be our example number 3. So h of x is, you're going to see this one from time to time. So I want to make sure you remember it, how to do it. You see sine inverse of the radical x. So the radical x, we call it u. So it's going to be sine inverse of u again. You know, if you want to practice, you can write the formula, you don't have to. So the solution is going to be, so your u is radical x. So you're just having what? So this h of x, which is the sine inverse of radical x, you have to treat it as sine inverse of u again. So the formula that you're going to use is the chain rule type. H prime is equal to u prime. That's 1 minus u squared. I just repeat the formula, you don't have to. Okay, so u is radical x, u prime, you know that. U is radical x. U prime derivative of the radical x is 1 over 2 radical x. Okay, you know that it's x to the 1/2 is going to be 1/2 x to the negative 1/2. That we write it down in this, in this format. So just memorize this one, and you're going to use it. Now, if you substitute, u prime would be what? U prime is 1 over 2 radical x divided by the square root of 1 minus u squared, 1 minus radical x all squared. Okay, I just substitute here. So the u prime is 1 over 2 radical x, that's u prime, and 1 minus u squared, 1 minus radical x squared. So you have to simplify it. The top one would be unchanged, and this is going to be 1 minus x, because radical x squared. You can bring that to radical x down. So h prime of x is 1 over 2 radical x times radical 1 minus x. You can keep it as is, or you can multiply the radicals. If you want to multiply, the two would be here, and x times x minus 1, x times 1 minus x. Okay, so that would be the final answer for sine inverse of the radical x. Okay, very popular formula, very popular one. So make sure you know how to handle it, and you have to go through the chain rule to get this one done. So u is radical x. So it's, the formula is the same. It's u prime radical 1 minus u squared, but you have to find u prime. It's a radical x, u prime would be 1 over 2 radical x, and we simplify to get through it. Okay, so that's a differentiation. You don't have anything else. These are the most popular one that we are going to be interested in. But the nice thing is the other way around. So pay attention to the other way around, integration. Okay, so it's going to be integration about. Here you are, we want to evaluate each integral. Evaluate each integral. Let's see what's going on with this one. Okay, and so the formula that we are going to have as I talk about it is going to be this form. Okay, the first one is integral of, you get 1, for example. Okay, 1, and this is going to be, this is the standard. I just give you the standard one first. You see, you want to find a function whose derivative is 1 over radical 1 minus x squared. That function is sine inverse. So the solution is going to be, that's just the formula. 1 minus x squared, okay, is going to be simply sine inverse of x plus c, and you're done. Okay, so this is just the formula that we memorized. So what's going to be the other option? The other option is like this one. You may have something like 1 over the square root of 1 minus 4x squared. You see? Your formula is just x squared. So you have 4x squared. When it's a 4x squared, it's like u squared. So you have to go through the chain rule type of this formula. So you have to take the u, okay, you take the u squared to be 4. You see, this is going to be how we handle it. Solution. You see, that's 1 over 4x squared. You think about it as, you don't have to write it, just explain it. So this is the way you think about it. You say, oh, this is like 1 square root of 1 minus 2x squared dx. So this means if you take the u to be 2x, that would be u squared. Then you'll be able to do it by substitution method. Okay, so if it's going to be just x squared, you're done. It's going to be sine inverse of x plus c. Anything else, you have to change it to the u. When you change it to the u, same formula. So we have a little bit more to do. So what is that? You take the u to be 2x. So you go through your substitution method. By the substitution method, you find the du. If of the 2x is 2, remember, times the dx. Then you have to find the dx. So we get the dx, which is going to be the du over 2. So go back substitute. If you go back substitute, you must end up with integral of 1 over the square root of 1 minus u squared. Okay? So we take it from here. We substitute for the u and the dx and be sure that we get the du part. Okay, so I'm going to repeat it. That's it. So the integral in question is this one. Integral of 1 over the square root of 1 minus 2x squared dx. That's what we are talking about. Substitute. So 1 the square root of 1 minus u squared. Because the u is 2x. Now the dx. Remember the dx was what? Dx was du over over 2. See? Dx is du over 2. So we substitute. So that would give us du over 2. There is nothing to simplify. So the extra number is 1/2. You can pull it out. It's going to be 1/2 integral of 1 over the square root of 1 minus u squared du. You see? So we change it to the format of the sine inverse. So this is going to be simply 1/2 sine inverse of u plus the constant c. But you have to go back and substitute for u. U was 2x. So that would be 1/2 sine inverse of 2x plus the constant c, and you're done. Again, you may have to do this one, in several places. So get to know them. So as soon as you see anything other than the x here, you have to go to the u substitution. And you switch it into this format, 1 over radical 1 minus u squared. There's going to be an extra number, doesn't matter. In this case, the number is 1/2. We put it out, and eventually we end up with the notion of the sine inverse to get these numbers. Okay, now there is one version that it's not going to be in your book, so we are going to explain it. You see, in this formula, look at this one. The formula starts with the 1 here. 1 minus x squared, which is sine inverse x plus 1. Sometimes they may not give you 1. They may give another number, 2, 3, 4. So if it's going to be that number, you have to normalize it. You have to change it to the 1 to be able to do it. So you can, you have to take a kind of factoring to be able to do it, to change it. So I'm going to give you a general formula. So you better memorize this one for integrating the sine inverse. Okay, this is it. If you have something like integral of dx, integral of dx, but instead of the 1, you may have a minus, okay, let's say a squared minus x squared dx. Okay, if you have the a squared, you can factor out the a squared. And when you factor it out, that would be x squared over a squared. So your u would be x over a. And this integral eventually is going to be equal to the sine inverse of x over a plus the constant c. But this a must be a positive number. You see? That's a much more general formula. The one that we did, a was equal to 1. If a is equal to 1, so that gives a sine inverse of x. So if it's going to be anything else, you call it a squared, you take the square root to get your a. Then you put it here. Okay, so we give you the formula so you don't have to factor it and do it. And of course, it can have in the u form. You can have the du, and this is going to be the square root of what? It's going to be a squared minus u squared. It's the same thing that gives you sine inverse of u over a plus the constant c. Of course, this a is positive because you have to take the square root of the a squared. So you may get a positive negative solution, but we're just checking one solution only. Okay, so these are going to be the most general form for the integrations. Let's give you an example, the way we're going to do it. That's it, example, and you have all of them in your practice quiz that I posted for you. So, and we are going to go over that one too. So what is going to be the example? We want to evaluate this integral. Evaluate. Okay, evaluate each integral. And the first one, you may have the integral of a dx over the square root of 9 minus x squared. You see this one? It is a form of the sine inverse. The sine inverse is 1 minus x squared. But here is 9, so that's it, this format. So a squared is equal to the 9, so a would be 9, a would be 3. So the solution is going to be solution. So we say the integral of a dx over radical 9 minus x squared is equal to, I just remind you that a squared is 9, so a would be 3. So according to our formula, it's going to be sine inverse of x over a, x over a, x over 3 plus the constancy. And then you're done. See, compare it here. Here you are. So a squared is 9. You take the square root, it's going to be 3. Sometimes it's not going to be a perfect square. So write it down in radical form. Okay, it was 3 minus x squared. You write the radical 3. That would be fine. Okay, so make sure you don't miss it. When there is a number, you have to divide by this number, sine inverse of x over 3 plus c, and then you're done. Okay, give you another one. Integral of the dx over the square root of, let's say, 5 minus x squared. You see, a squared is 5, so a would be radical 5. So the solution is going to be, so the integral of a dx over 5 minus x squared. Again, I remind you that a squared is 5, so a is radical 5. So this would be sine inverse of x over radical 5 plus the constant c, and do that. We don't simplify it, we don't rationalize the denominator. We just write it down as is. I mean, as the radical 5 that we have. Okay. Any question? So make sure you know this format. I give you one in this form, the most general one of these type of problems. This is where you have to do your substitution and this format at the same time. So this is the kind of most general problem that we have. What is this? Look at this one. It's integral of dx over the square root of, let's have 25 minus 9x squared dx. You see this one? You see, this is of the form of the sine inverse, but this is not x squared. You see, you would like to have 25 minus x squared. It's 25 minus 9x squared. So you have to change it in the form of 25 minus u squared. So you have to do the substitution and then, change it. So the solution is going to be, you have a little bit of extra job. So this is what you're going to do. You take the u to be 3x, because that's a 9x squared. You have to do the substitution. Du is 3dx, and the dx is du over 3. So you do the substitution first to change this one into 25 minus u squared. When it's a 25 minus u squared, you can use that formula and then you'll be done. Okay, so go back, change it. So this is going to be a dx, and this is the square root of 25 minus 9x squared. So your dx is going to be the du over 3. Okay, and the square root of a 25 minus, now it's going to be minus u squared. See? There is nothing to simplify, but a 1/3. A third is extra number, you put it out. So that gives 1/3 integral of the du over the square root of what? 25 minus u squared. See, your a squared now is 25 and you can continue. So we got to be careful. If it's going to be x squared, you can do it right away. No substitution is needed. If it's going to be anything else, you have to go with that substitution. So now the rest is going to be, you don't have to write this, but I just explain it. You remind yourself that the a squared is 25. So you take the a to be equal to the 5. Then you continue. So it's going to be 1/3 sine inverse u over a. U over a. What is a? A is 5. Plus the constant c. And you have to change the u. What is the u? U is 3x. So the final answer is 1/3 sine inverse. Okay, 1/3 sine inverse of the u, which is going to be 3x. 3x fifth plus the constant c. And then you're done. Okay, it's a kind of the most general problem that we can have for this inverse trigonometric function so far. There is one more tricky one. We'll talk about it later. Okay, now we go through it first. You don't have it in your book, but we need it when we get to the chapter 7. But we take care of it later on. Okay, so this is the sine inverse. Okay, the derivative of the sine inverse and all the explanation to get to the integrations. The next interesting inverse function is tangent inverse. Cosine inverse is not very interesting because if you remember from your pre-calculus class, there is a relationship between the sine inverse and the cosine inverse, because you see the sum, you know that if the sum of two angles is going to be 90 degrees, so the sine of one of them is the same as the cosine of the other one. So there is a formula quickly between the cosine inverse and the sine inverse that would end up with this one. So I just show you, but we are not going to use it. That's why we are very much interested in the sine inverse really. You see, the remark is going to be this one, that we can prove that cosine inverse of x is equal to the pi half minus sine inverse of x. It's a famous problem in pre-calculus. So if you differentiate it, so if you want to find the derivative of a cosine inverse of x prime, derivative of the pi half is 0. It's going to be minus the derivative of the sine inverse. So derivative of a cosine inverse of x is going to be minus 1 over a square root of 1 minus x squared. You see? That's why in calculus, this is not popular. Because if you want to integrate it, you see, if you want to integrate negative 1 over radical 1 minus x squared, you know that you can keep this negative sign and you integrate this one. So that's why it's not going to be used, and we don't have to worry about it for the cosine inverse, because everything will be like the sine inverse. Okay, so we are going to be confused if you like. So that's why you see the most problems related to it. Okay, so it's nice to know this formula, but it's very similar to the sine inverse, so I'm not going to use it, but if you see it in your book, this is the derivative of a cosine inverse. Okay, so it's going to be the sine and the cosine, but the most popular one for calculus 2 is tangent. So what is going to be the tangent inverse? Okay, tangent inverse function. Okay, so we get to that tangent inverse, and you can have it, in your book, the same one. I'm just checking. Again, you can argue. Okay, you can argue about where this function is going to be defined. We can do the same thing as we did it for the inverse function, but I'm going to introduce this one right away. Okay, so the inverse tangent function, or tangent inverse function, it was the other way around. The inverse tangent function, again, is denoted by y equal to tan inverse of x. We are not going to use the sign arc sign, but if you see it, it's the same thing. Arc of the tan x. I avoid this notation. It's going to be not a precise one, and is going to be defined by, and is defined by, same thing like the sign. So the y equal to the tan inverse of x implies if and only if x equal to the tan of y. Okay, you just switch it. Again, it's going to be the same thing, that the y is going to be between negative pi half and the pi half. Okay, even it can be equal to, but this, and the x is going to be, you know that the tangent of the pi half is infinity, or it's undefined. And the tangent of a negative pi half is negative infinity. That will tell you that this is it. So your x is going to be between negative infinity and positive infinity. So the domain of that's why this is popular. So y is equal to the tan inverse of x, okay, where x is going to be between negative infinity and positive infinity. So the domain of the tan inverse is all real numbers. So that's why this function is such a popular one for the application, because it's defined everywhere. Okay, it's defined everywhere. So we can differentiate this equation to get the derivative. I just write the derivative of this function for you right away. Okay, we write it down as a theorem. That's it. Derivative of the tan inverse of x is 1 over 1 plus x squared. Okay, that's going to be the case. You differentiate both sides and you get it. And if you have the u function, so the tangent inverse of anything other than the x, again, you have to multiply this one by u prime, the chain. Okay, so the derivative of tangent inverse of x is 1 over 1 plus x squared. That's going to be tangent inverse of x squared, 2x, 5x. Then you have to multiply by u prime because of the chain rule. And of course, equivalently, you have the integration. Equivalently, that the first one would be changed into integral of 1 over 1 plus x squared dx is always tan inverse of x. And the second one, the same thing. So if you have the u prime dx, or just if you have a 1 plus u squared, the u is going to be tan inverse of u. So sometimes you may have to use substitution method. Okay, so if just the x squared, it's done. It's going to be tan inverse of x plus c. It's going to be anything else, you have to call it u first. Okay, you call it u, and then you end up with the tan inverse of u. Very popular when we get to the chapter 7. You'll be surprised that in many integrations that you are going to do for us, you may get this one. Okay, very popular. So we get to know it. 1 plus 1 x squared is the derivative of tan inverse of x. So this integral would be tan inverse right away. Okay, again, this is 1, but you may have this one equal to the 5, equal to the 6, equal to the 9. Then you have to factor it out. So there's going to be a procedure similar to the sign. So what I'll do, I'm going to give you as a formula, you memorize it, and you don't have to worry about it. So if you have something like 1 over, I give you the last one. It's going to be a squared plus u squared. If it's going to be a squared, you have to factor it. In this case, it's going to be 1 over a tan inverse of u over a plus the constancy. Remember, in the case of the sine inverse, there is no 1 over a. But in the case of the tan inverse, there is. And the reason is, in the case of the sine inverse, there was a radical involved. And remember, look at this formula that we did. You see, this is the one that we did over here. It's a kind of radical a squared. That's why, this and the u substitution that would disappear. But here is, there is no radical, so you have to have 1 over a. Okay, so if you compare them together, the other one would have these extra factors that we get it. Very popular formula for the when we get to integrating the rational functions. Okay, so one of the questions in your quiz is going to be 2 parts. The first part you differentiate just using okay, differentiate when we get these okay, we get the tan inverse function, and the other one is just the integrations. So to give you an example, I'm going to do it. The other inverse functions are not popular. We give you the derivative only the secant inverse, but not the integration. So let's take care of this one first. So example, the first one, differentiation. Okay, find the derivative of each function. Okay, so the first one, no chain rule, it's just the powers of x, something like x to the 4th tan inverse of x. There is no chain rule involved, but you have to use the multiplication rules to get these numbers. Okay, so that is going to be the case. Okay, it's a product of 2 functions. The first function is x to the 4th. The second function is what? Is tan inverse of x. So we have to apply the product rule. Derivative of the first times second plus derivative of the second times first. Okay, so let's do it. Okay, so this is going to be kind of the first function. So you see, that is the first function, and this is going to be our second function. So we are going to apply the product rule. Derivative of the first times the second plus derivative of the second times first. Okay, that's the formula. So now let's do it. So it's going to be solution f prime of x is equal to. Okay, it's going to be equal to the derivative of the first one. Derivative of x to the 4th is simply what? 4x cubed times the second one, tangent inverse of x. Okay, so that would be the derivative of the first times the second plus derivative of the second times first. Derivative of the tangent inverse is what? 1 over 1 plus x squared. That's the derivative of the second one. Times it by the first one. Times it by x to the 4th. Nothing to be simplified. So it's going to be f prime of x equal to 4x cubed tan inverse of x plus x to the 4th over 1 plus x squared. That would be the derivative of the function. You cannot simplify it. So that's the best you can do. Okay, so it's a product of 2. As I did it, you see, you can have x to the 4th times sine inverse or the tangent inverse. These are very standard operations that we are going to have. So derivative of the first one is 4x cubed times the second function, tangent inverse, plus the derivative of the tangent inverse times the f of a tangent inverse. We have the formula here. See, the tangent inverse of x, your derivative is going to be 1 over 1 plus x squared. So that would be derivative of the second one, 1 over 1 plus x squared times the first function. You cannot simplify it, so that would be the end of the problem. Okay. The second example is the one that you have to apply the chain rule. F of x equal to tan inverse. Let's say tan inverse of 5x. You see that's what. You see it's not x, it's a 5x. So you call it u equal to the 5x. Okay, you have to use the chain rule. So we take your u to be 5x. So remind yourself that, so your function is what? Your function is tan inverse of u. So what's the derivative of this function? You have to apply the chain rule. So it's going to be u prime over 1 plus u squared. Because the derivative of the tangent is 1 over 1 plus u squared. And you have to multiply by u prime. Now substitute f prime of x equal to u prime. U is 5x. So what's going to be u prime? U prime is 5. So it's going to be 5 on the top. 1 plus u squared. U is the 5x. So it's going to be 1 plus 5x squared. Okay, so f prime of x is going to be equal to, we got the 5 on the top, 1 plus 5x squared. 5 times, it's going to be 25x squared. And then you're done. Okay, so be careful when it's not x, you have to use the chain rule. The chain rule is just a combination, a composition of two functions, tan inverse and the u function. Tan inverse is 1 over, you see 1 over 1 plus u squared. But you have to pay for it. You have to multiply by u prime. U prime is 5. So that gives you the final answer. Okay, so this is just the two sort of differentiation that we're going to have. Okay. But again, dealing with the radical function, this is a very popular problem. I did it for the sine inverse. I do it for the tangent inverse too. This function is very popular. Okay. The tangent inverse of the radical x. You want to differentiate it. So you have to take this one to be u. So you have to use the chain rule again. Okay, so the solution is going to be, you remind yourself that I take the u to be radical x. So I have the gx equal to the tan inverse of, okay, the tan inverse of u. Again, you don't have to, but you can, prepare yourself by repeating the formula. U prime over 1 plus u squared. Now substitute. U prime, derivative of the radical x. We talk about it's going to 1 over 2 radical x. That's u prime, derivative of the radical. It's going to be x to the 1/2. It's a 1/2 x to the negative 1/2, which is the same thing. Okay, memorize this one. 1 plus u squared plus 1 plus u. U is the radical x, so it's going to be radical x squared. Now you have to simplify it, so it's going to be g prime of x equal to, at the top one we keep it, 1 over 2 radical x. The bottom one would be 1 plus x. We can bring this one down. So g prime of x is 1 over 2 radical x times 1 plus x. This would give you the final answer. You don't have to multiply inside. if you like, you can do it, but you don't have to. Okay, so this is going to be the derivative of the tangent inverse. I'll just give you the examples that's going to be used, in future quite a lot. So we don't have to go through very complicated one. Okay, we just take the one that we need. Okay, now examples on the integrations, which is much more interesting. Look at these examples. All of them are going to be used in future. So, example, like to integrate. So evaluate each integral. The first one is just the usual one, just to remind you. Integral of dx on the top. And this is a 9 plus x squared. You see, you know that this is of the form of the tangent inverse. It's 1 over a squared plus x squared. Your a is 9. Okay, and you can use the formula right away. Just remind you the formula. You see, this is the formula. Dx over a squared plus x squared is 1 over a tan inverse of x over a plus c. That's your formula. Okay, so your a is 9, a squared is 9. So the integral of a dx over 9 plus x squared, remind yourself that a is 3 if you like, because a squared is 9. So 1 over a is going to be 1/3. Okay, 1/3 tan inverse of what? X over a, x third plus the constant c, and you're done. Okay, it's very easy to identify this formula. In the case of the tangent inverse, it's very easy to identify because the bottom must be of the form of a squared plus x squared. Okay. Most of the time, these numbers may not be a perfect square. So you may have this one, 2 plus x squared. Again, is of this format. So your a squared is 2, so your a would be a radical 2. Okay, so the solution, just remind you that your a squared is 2, so your a is a radical 2. So what's going to be the formula? Dx over 2 plus x squared. Remind yourself that the a is radical 2. So 1 over a, 1 over radical 2. Tan inverse of x over a, x over radical 2 plus constancy. Do that. We don't usually to simplify it, especially this one. We are not going to move it up. So that would be, you can simplify this one if you like, but that would be acceptable as the final answer. Okay, so that's going to be the type 1. No substitution is needed because that's x squared. Now, if this is not going to be x squared, you have a little bit more job to do for us. So if you have something like a dx, and that would be 16 plus 25x squared. You see, this is a squared plus. It's not a squared plus x squared. It's you have to call this one u squared this time. So it's like 16 plus u squared. So you need to do the substitution method. Okay, so if it's going to be x squared, you're done. That's anything else. You have to bring the u, do the u substitution to change it into the 16 plus u squared. Okay, so a little bit more job to do. So there you are. You take your u to be 5x because that's a u squared. Then you do the substitution method. du is 5 dx. You have to find the dx. So the dx would be du over 5. Substitute. Remember what's your target? Your target is you like this one to be 16 plus u squared. So it's a dx. And that would be 16 plus 25x squared is equal to, okay, dx is just a dx, 16. Oh, I'm sorry, I have to substitute for the dx. The dx is the du over 5. That's a 16 plus u is the 5x, so this would be u squared. Okay, the dx is a du over 5. That's a 16 plus u is 5x. So you cannot simplify it a fifth, you can pull out a fifth. And then you get what you are looking for. Look at this one, du. 16 plus u squared. That's it. A squared is 16, a is 4, and then you continue. So remind yourself that the a is equal to 4. So this is going to be a fifth. Now the formula was 1 over a, 1 over 4, tan inverse of u over 4. u4, okay, plus c. You have to simplify it. 5 times 4 would be 20. 1 over 20. Tan inverse. You substitute for u. U is 5x. 5x over 4. Okay, plus the constant c. The final answer. See, very nice integral. And we can easily operate to get these very popular cases for the integration that we have. Okay, so get to know it. It's going to be repeated over and over and over, for the rest of the course. But quickly take care of it, to identify it. So I give you a couple of more to get a tricky one that you don't have it now in your book, but you have it in future. Okay, let's start with this one. So that was a number 3. So let's have number 4. Then I give you the actual one. See, look at this one. Suppose you have the dx here. X, and we have a 16. You have something like x plus 5 all squared. Okay, this one. So you can call x plus 5 u. So it's of the form of like a du over 16 plus u squared. So that would be the tangent inverse type. So for this one, what we can do is we can take the u to be x plus 5. Substitution method. You have to find the du. The derivative of x plus 5 is just 1, so we get the dx. Go back and substitute. So we have the dx, and this is going to be 16 plus x plus 5 all squared. So it's going to be equal to, the dx and the du are the same, so it's going to be du. And this is going to be over 16 plus, and this is going to be u squared, you see. So that would be tan inverse type, a squared plus u squared. A squared is 16, so a is 4. And the formula, remember, 1 over a, 1 over 4, tan inverse of u over 4, plus the constant c. And what is u? X plus 5. So it's going to be a quarter tangent inverse of x plus 5 over 4 plus the constant c, and then you done. See, that give you the result of your integration to get these numbers done. Okay. Now, there are a group of problems in future that can be solved by this formula, and this is just to give you an idea for future. This is one of them. Look at this integral, dx. Okay, so on the bottom, I am going to have the x squared plus 4x. Okay, this is going to be x squared plus 4x, and I've got something like a 5 here. I have to calculate something to get I should get it right. Yes, 5 would work. You see, look at this one. Dx over x squared plus 4x plus 5. It's a very special function. So what we do in future is we try to factor the denominator. You have x squared plus 4x plus 5. If you want to factor it, you know that you need two numbers with the product of 5 and the sum of 4, which is not possible because the number with the product of 5 is 1 and 5. But if you add them together, we get 4. So this means this denominator is not factorable. It's not going to be factorable. So what you are going to do for integration, you have to use the tangent inverse to do it. But in order to get the tangent inverse, you know that this must be of the form of a squared plus u squared. So a little bit of algebra, you have something in algebra, we call it completing the square method. This is where we are going to use this one. You see, this is x squared plus 4x plus 5. So what we're going to do is we are going to write it down as a squared plus u squared. So the way we are going to do it, we make a perfect square from here. So what we do is we divide this coefficient. You do it in your college algebra or free calculus. We divide this one by 2, so that gives you 2. So we write this one as x plus 2 all squared. You see? But when you square it, that gives you x squared, twice of the first times second, 2 times 2, 4 times x, 4x, plus 2 squared, which is 4. There's no 4 here. So that's why you subtract the 4. Okay, this is a procedure that you use in algebra to completing the square method. It's very easy. You divide this coefficient by 2, that gives you the second number. It's going to be x plus 2 all squared. But when you square it, x squared, twice after first times second, 2 times 2 times x, 2 times 2, 4 times x, 4x. But it's going to be plus 2 squared. 2 squared is 4. You don't have the 4 here, we subtract the 4. But there is a 5 here, we simplify. You see, if you add them together, that gives you x plus 2 all squared plus 1. If you rewrite it, you find out that you can do it with the tangent inverse right away. It's going to be dx, and this would be 1 plus x plus 2 all squared. It's like this problem. It's much easier, of course, because you take the u to be x plus 2 is just a dx over 1 plus u squared, you see. You take the u to be equal to the x plus 2, the du and the dx are going to be the same. So this integral would be equal to, we have the dx, 1 plus x plus 2 all squared, and that gives you the du over 1 plus u squared. And you know that this is simply tan inverse of u plus c. You substitute for u, tan inverse of x plus 2 plus c, and do that. You don't have it now in your book, but you will see it in chapter 7. Okay, in a few sections of that chapter, you have to take care of this type of problems. Okay, so if you don't like it now, then we are going to see it again in future. So that's why I wanted to say it. So the point is that if this is going to be factorable, you can do it. We have a method for it later on. But it's not going to be factorable. It must be done by the tangent inverse. But you have to switch this one into kind of, u squared plus, like this one, a squared plus u squared. In order to do it, just make a completing the squared, divide this coefficient by whatever number it is, so that gives you x plus 2 squared. But when you square it, x squared, 2 times first times second, 4x, there's going to be a 2 squared, which is 4. You don't have the 4. You subtract the 4. So always is like minus b squared. This is b minus 4. And the 5 and the substitution method give you the final answer right away. So as you can see, the tangent inverse is the tricky one. It's the one that we like it. We love this one for future. It's a very strong tool among the inverse trigonometric function. Okay, that's going to be the tangent inverse. The cotan is very similar. It's a minus this one. We are not going to do it. I just give you the derivative of a secant inverse. Okay, we don't need anything else. So this is going to be the inverse secant function. Inverse secant function. Okay, and as usual, it's going to be denoted by, it is denoted by y equal to the secant inverse of x, and is defined by y is the secant inverse of x if and only if you switch it, x equal to the secant of y. Okay, so the definition is going to be the same as you did for the other one. If you differentiate both sides, that gives you the derivative of a secant tan. So that's why your derivative is going to be, so it can be proved, if you like, that the derivative, this is the formula that you have to memorize, derivative of the sine inverse, secant inverse. Secant inverse of x is 1 over x radical x squared minus 1. It's in fact radical, it's absolute value of x. But we assume that the x is positive and we use this formula. And for the integration, it's going to be complicated and we have some other methods to do it in future. So that's why I just wanted to know the derivative of this function, nothing else. So if it's going to be u, as usual, u prime on the top. Okay, so because there are a couple of problems in future that we are going to use the derivative of this function. So make a note, make a formula sheet if you like, just put them the derivative of a secant inverse as well, so that in case we are going to use it. Okay, just one example, and this is all we need for the inverse trigonometric function. Okay, so example, find the derivative of each function. Okay, derivative of each function. That's it. As usual, the first one is going to be something like kind of product x squared secant inverse of x. Okay, we apply the product rule of the first times second, second first. No chain rule is going to be used. Okay, so and this is it. F prime of x is equal to divided of the first one, divided of the x squared, of course, is 2x times the second one plus divided of a second times first, second, divided of a secant inverse, 1 x radical x squared minus 1 times the first one times the x squared. That gives you always the chance to simplify it. That gives you x. So f prime of x is the 2x secant inverse of x plus x over radical x squared minus 1. And then you're done. Okay, just for all of them, one case is going to be, the product rule, derivative of the first times second, second first. Okay, and the other one is, of course, the chain rule type. So let's have a g of x equal to the secant inverse of x cubed. So you have to take the u to be x cubed and use the chain rule. Okay, so for this one, you have the u to is equal to the x cubed. Remind yourself that's going to be g of x equal to the secant inverse of u. So your formula this time is going to be u prime, u radical u squared minus 1. Just remind you the formula, you don't have to write it and write it down. Okay, so u is x cubed, so u prime is 3x squared. So g prime of x is going to be equal to 3x squared, u x cubed, the square root of u squared, x cubed squared minus 1. Now the x squared would be simplified, that give you x. So the final answer is 3 on the top, x radical, x to the 6 minus 1. The final answer. Okay, so that gives you the derivative of a secant inverse. Cosecant inverse, again, is very similar. There is just a negative sign over here. That's why they are not going to be used. Because in the case of the integrations, you don't need it. Because, that negative sign up in front won't do anything for us. So that is what we need from this section 6.6, inverse trigonometric function. So we are ready for, we cover all the topics that we need for the coming quiz. There is one more section from this chapter. I may talk about it, but I'm not going to give you that one on the quiz because I want to give you enough time to prepare yourself for the quiz. So I will post another recording for you by the end of the week. And that would be, I go over some of the problem of the practice quiz that I posted for you, okay? There's going to be a take-home extra point for that to prepare you, and the actual quiz that's going to be, I may post it by the weekend. Then you can submit it by, I think, next Tuesday is the time for your quiz. I double check it, the date, but we are ready for it. And the assignment is going to be due again. These are the ones that I already posted for you. Okay, for the homework number 1. So make sure that watch this video, okay? And if you have any question, just let me know. Any question, if you want office hour, just email me, we can arrange it for you on Zoom. Okay, so get through these topics. As I told you before, they are going to be the tools for the chapter 7. We have one more section to go. That's 6.8. That's going to be Hospital rule in determinant form. We are going to use it for the second part of the course quite a lot. So we take care of that one too before getting to the chapter 7. Okay, so your target is this week to finish these concepts. So you have 4 concepts. Substitution method, okay, exponential function, e to the x, derivative and integrations, natural log function, derivative of integrations, and inverse trigonometric function, derivative and integrations. So we get 6 questions from this, okay? So we'll just give you a couple more days so that you prepare yourself. Okay, that's it. I will post this one right away. Have a good one and take care and let me know